Right, so what determines the shape of molecules? It is really simple. Um, so if you want to see the demonstration, look at the Vesper 1 and Vesper 2 videos. But really the idea is that electron pairs, whether they are unshared pairs or shared bonding pairs, they're sets of electrons. They have negative charges, and as such they repel each other, so they want to be as far away from each other as possible. So if you wanted to determine the arrangement of the electrons around a particular atom in a molecule, the question you want to ask yourself is, what is the shape that maximizes the distance between 2, 3, 4, 5, or 6 mutually repulsive objects tethered to a common center point? And it turns out that there are shapes that do that. So again, watch the video. For 2, the best arrangement is linear. So having these sets of electrons, these electrons domains as I call them, 180 degrees away from each other, represents the furthest apart they can get. Now the magic shape for 3 mutually repulsive sets of electrons is 120 degrees away from each other. They're all still in the plane because, well, there's only 3 of them, and by definition they're still in the plane. So these kind of form an equilateral triangle, and this shape is called specifically trigonal planar. Now the magic number for 4 is the tetrahedron that we just saw in the last video. Now we are going into 3 dimensions, as you can kind of see from this picture here, and each of the angle between any of the 2 electron sets or electron domains is 109.5 degrees. The shape that gets 5 mutually repulsive objects as far away from each other as possible is something called a trigonal bipyramid, or a trigonal bipyramidal shape. And this has 3 of the electron domains that are 120 degrees away from each other, and they are still in the same plane. So if you're looking at this on any type of normal computer screen, you can think of these as being parallel to the plane of the floor. And then you've got one set coming out from under there, kind of out of the middle, and then one going down. And finally, 6 sets of electrons, which is the largest chemically relevant number. That magic shape is something called an octahedron, or an octahedral shape. So octahedron means you've got 8 faces. There are 6 sets of it. 4 of them are 90 degrees to each other. They form a square. One comes up, one comes down. So these are the shapes that maximize the distance between 2, 3, 4, 5, or 6 sets of mutually repulsive objects tethered to a common point. And watch the balloon video if you don't believe me that these are the appropriate shapes. All right, molecular structures. So we're actually going to talk about 2 different types of structures almost simultaneously here. Number 1 is the electron pair geometry. So this is the arrangement of the electron domains around a particular center. And again, I use the word electron domain as a general term that describes shared bonding electrons and unshared electrons as well. The second one is going to be the molecular geometry. So this is the arrangement of atoms around a particular center atom. And it's the shape that those molecules actually adopt. All right, and the next, let's say 2 videos, actually I'll get started. I'm going to talk about all the various possibilities that we've got going on here. So the first set, we're just going to work our way. We're going to start from 2 sets of electron domains and work our way up. All right, so as we discussed, if you have 2 sets of electrons, the geometry that those electron domains are going to adopt is linear. And the molecular geometry is also going to be linear. It's the same thing. So as an example for this, I've got beryllium hydride and carbon dioxide. I'm going to do carbon dioxide as an example here to point out this one thing that multiple bonds count as one domain. So if you look at if you do the Lewis structure for carbon dioxide, you should get something like this. That you've got two double bonds on the carbon to each of the oxygens, and each of the oxygens also has an unshared pair. Now what matters is the number of electron domains around the center atom, in this case the carbon. Now it turns out that when you've got double bonds like this, it's not really two distinct sets of electron density, like one up here and one up here, one up here, one down there. They're kind of all blobbed together. It's just that instead of 2 electrons in that space in between the atoms, now there's 4. So it looks something like this. So essentially they count just as one domain, so not 2, and triple bonds don't count as 3. All right, so that's linear. So and those are the only possibilities if you have 2 sets of electrons. So the next possibility is if you have 3 electron domains. So the magic geometry for the electron domains is the trigonal planar structure that we just talked about. And the molecular geometry, you actually have a couple of possibilities. So in one case, the molecular geometry could be trigonal planar if you've got something like boron trihydride. So here's an example. So if you were to do the Lewis structure for boron trihydride, you should give me something like this. So remember, hydrogen was one of the easy elements because the only thing it can really do is make single bonds. Now, if you're looking at this and saying there's something weird about this structure, there kind of is. What is it? The boron doesn't have a full octet. But that's okay. The rule is that the second row elements can never exceed an octet. And in some cases, particularly with the elements that don't have a lot of valence electrons, like boron and beryllium, that you just really can't do it without having some really, really heinous formal charge. So this is an underfill octet. Boron does that. So you've got 3 electron domains, and so they're also going to adopt a trigonal planar structure. But there's another option. And all these, and before I get going too far, all these bonds are exactly the same, and they're all going to be, the angle's going to be 120 degrees, and this thing is planar. So all 4 of these atoms are in the same plane, which in this case would be the plane of the screen. But you could have something like our friend ozone that we studied about with resonance a few videos ago. The Lewis structure we came up with for ozone, I didn't get the shape right here. I purposely didn't put the shape in yet. Something like this. You've got 1 oxygen-oxygen double bond and 1 oxygen-oxygen single bond, and you also have an unshared electron pair on the oxygen in the middle. Now, remember what we said about multiple electron domains. So this actually counts as 3 electron domains. There's 1, there's 2, there's 3. So all those electrons are going to adopt a trigonal planar structure around that central oxygen. It would sort of look like this. So this is one of the oxygen-oxygen bonds, this is the other one, and this is the unshared pair. Now what you want to do is imagine what the shape is if those electrons actually weren't there. So if they were just erased out there, what name would you call the shape that the oxygen atoms themselves adopt? And so they're not in a straight line. So the name we give to that shape is, imaginatively enough, bent. So the atoms are bent, so that they're not in a straight line. All right. And I'm going to do one more before we split the material up. But before we do that, one other piece of information. So unshared electron pairs take up a little more space than bonding pairs do, which means that this angle is actually going to be a little bit less than 120 degrees. Now, you don't need to know exactly how much less, but you do want to know that it is, it's a few degrees less than the perfect 120. All right.